Hello everybody and welcome to another new repair. Today I have a Battlezone board set. This comes from Chad in New York. I just got this one out on the bench and hooked up. And happy Valentine's Day everybody, by the way. Today is February 14th. And you can obviously see my current status because it's Valentine's Day and I am working on a Battlezone board set. So anyway, okay, yeah, I just got this one put on the bench. This board set is really super dirty. I mean, I think that's supposed to be black. Look at that. Yeah, this is a really, really dirty board set. Original sockets everywhere. That is going to be a big problem right there. I haven't done anything. I haven't reset anything. This is as found condition right here. This is right out of the box and hooked up. And we're going to go ahead and see if this thing does anything. Before I do, though, I do need to check all the make sure nothing's shorted to ground. So let's do that first. Okay. Just gonna test continuity to ground at some of the test points. Make sure we're not shorted to ground on this guy. So I'm going to hook one lead right to the ground lug and then just go around to the various points. That's ground. So we are not shorted out to ground. Z out for some reason is always short to ground. Hold on a sec. That is +5. +5 is short to ground. Okie dokie, we have a huge problem here. 5 volts is short straight to ground. Every 5 volt lug on here is right to ground. So we're going to have to find out what is shorting 5 volts to ground. I'm going to put it on ohms and check ohms from 5 volts to ground. It should not be. It's a dead short. Now it's 42 ohms. $42 to ground. Strange. I'm gonna have to do a little research on that before I go firing this thing up. Okay, I'm going to unhook everything so that everything's isolated. Power supply's not in play at all. And then see what happens. See, I'm going to retest. Okay, I have completely unhooked everything. And this board is now not showing. Whoa. something weird's going on because it was shorting, now it's not. Okay, I'm gonna have to just look over this board really carefully because something funny's going on here. So that's what I'm gonna do. I'm gonna look it over really close. Okay. Something funny, something weird going on. Reset don't have nothing to do with that. Okay, I'm going to cut the camera off and I'm just going to get under my magnifier here and I'm going to really look this over. Something weird's going on and I just want to look at it real close. I wonder, yeah, got one of these. We got a couple tantalum capacitors up here. Okay, I'm seeing some funniness right here. I don't like this at all. There's some kind of weirdness going on here. Okay, there are two tantalum capacitors up here. There's some weird kind of residue up here by this regulator. So I think what I'm going to do first and foremost on this board is I'm going to recap it. Get rid of these tantalums. Before I go plug in, I do not want to blow my AR up and have to rebuild my AR. This thing's got flakiness going on. You know, I've been seeing some shorting and stuff like that. So I'm gonna go through and I'm gonna recap this thing. And then we'll go from there. We're gonna recap it and I'm gonna replace the regulators. Okay, I'll be back. Okay, I have recapped this board. Completely recapped it. And I did a test and it went from 47, 48 ohms or something like that up to like 53 ohms. So this is just a low resistance board from +5 to ground. So yeah, if it 50 ohms or under, I believe it will beep as a short. But I guess that's how it's supposed to be. So, okay, we're going to go ahead and fire this thing up. I'm going to get my voltage ready to go. I'm going to test the voltages. I did change all of the regulators as well. So, we'll see what happens. Hopefully this doesn't blow up. Ready? And we're on. Okay, 4.95 volts, that's good. And over here we'll go +12, we've got 11 something, which is pretty normal. -5 is -0.65 something or other. -1465. 1470. So we're looking good on all of our voltages. Okay. And what about 5 volts for the DAC? Here it is. And we're at 499 for 4.99 volts for the DACs. So we're good. Power is good. But we got nothing going on. This thing is dead. Let's see if we get anything in test. Not really. And let's grab our logic probe. Go from ground to 5 volts. Okay, and let's check out our CPU. Pin 40 is reset, and it is resetting. Okay. 1, 2, 3, 4, 5. Pin 6 is the interrupt, I think, on a 6502. So this looks like, and we're not getting no beeps. I don't remember if this game beeps at you if you got. I don't like that button. It's so sticky. It works. Okay. This could be just a bad socket problem too, you know. Yeah, definitely socket problem. I'm just going to, I'm going to go through and reseat all of the ROMs. Let's turn it off. And let's use this thing and just kind of reseat these guys. Don't have to take them all, just kind of rock them and push them back down. Vector ROMs. And let's turn it back on. And we're still, but do we get any further? No. I do have the right one hooked up, so that's okay. You know what I ought to do is let me check the power on this little board too. I did make sure it wasn't shorted out. And our 5 volts is 498, which is good. Plus 22 is 1880, which is fine. And there's one more. Negative 22, where are you? I don't know. Negative 22, where are you? I don't know. Who knows? Maybe negative 22 volts is not sent to this board. I don't know. There's no test loop for it. Not that I can see. So, okay, power's all good. We're good on power. So, we have a complete. This thing is not running any part of the code. So, what chip is that? Dusty ass thing. That is I think that's a 244. So, it's enabled. Always enabled. 2 out to 18. 17 out to 3. 4 out to 16. 15 out to 5. 6 out to 14. 13 to 7. 8 to 12. And 11 out to 9. That thing seems to be working right. But that doesn't mean it's working right. It's not obviously blown out. That's a 245, 245. Here's another 244. Always enabled. 2, 18. Okay. Okay. I mean, I know you can't really go by sound on this logic probe, but I would like to look at that because it looks funky. This guy right here is a 245. That's direction. This is enable. So it's always enabled. So if we have activity on one side, should have activity on the other side. Okay. All right. Direction. This guy is not ever enabled. And he may not be. In this state, it may not ever be enabled. Yeah. That this guy right here, I believe, is the buffer for the vector ROM and RAM. And it's not enabled. It's pulsing now and again. It's really kind of suspect because it hardly ever pulses, but it pulses now and again kind of erratically. It's kind of weird. Okay. I think what I need to do is I'm going to put my Fluke on here. I'm going to put the Fluke on here and go through my ROMs and RAMs. That'll tell me if, you know, that'll, ooh, that's getting hot. This thing's pretty damn hot. You're getting pretty hot for not doing anything. Right now I'm suspecting bad RAM buffer. And if the CPU cannot access the RAM, the vector ROM, or the RAM bank here, then it's not going to do anything. So, the decoding. I still don't think this is getting to these ROMs either. Because if this thing was able to run the code to do the testing, it'd give me, and this buffer was bad, it would probably give me errant RAM errors. So I'm thinking this thing is not reading code. Something's funky in the decoding and the buffering and stuff like that. So I'm going to hook the Fluke up to it and we'll go from there. Okay guys, I'm going through the Fluke here, doing some Fluke stuff with this board. And I'm looking at these RAMs here. And that range is 2000 to 2FFF. So if I go ahead and do 2000 to 2FFF and wait it out, okay, it's given me 244A. Bits 20 are bad. So it's telling me that the upper 4-bit chip is bad at this range. I'm going to just hit repeat and see if it does the same thing. Okay, it's not random. So we definitely have a bad chip. Okay. How do we figure out what chip that is? Without using a logic probe, without doing anything except for looking at the schematic and finding out what chip is in this range. Okay, well we have 8 2114s. 2114s, if you look over here, 2114s have 10 address bits. They're addressed 0 through 9. Okay? 0 through 9 is their address bits. So I got a little something done up here. I'll try to go through this of how you can, looking at the schematic, you can figure out ranges. So let me set this up here. Remember this, the 2114s, we do not care what these first 10 address bits are. Bits 0 through 9. They can be 1 or 0, doesn't matter. All they do is they address the chip. What's going to determine our range are these guys right here, 10, 11, and 12. This is always going to be it doesn't matter, because this is it does matter. This is trying not to get too crazy here, but this is always going to be 2 in this range. Yeah, in that whole RAM range, it's 2 something something, 2 something something something, like 2000 to 2FFF, So just don't worry about that. Now, these are the 4 signals that we're concerned with, because these signals right here are what activate our vector RAM. These guys are right here. The 4 lower outputs to this decoder. So that tells you this is the most significant bit, and it's grounded. It's always 0. It's only either going to be 0, 1, 2, or 3. So we know this is always going to be 0. 12 will always be 0 to enable those RAM. So it's either going to be up to address 10 or 11 is going to determine which ones are turned on. Just 10 and 11. 12 will always be 0. Because if the 12 goes to 1, it's going to access these guys. And those don't need to be accessed because they're non-existent. These are the only ones there. So 12 will always be 0, and it's going to be up to 10 or 11 to determine our range. So if we come back over, okay, where was I? Sorry about the interruption there. But what I was saying was, okay, 12 will always be low. Address bit 12 will always be low. And it's up to 10 and 11 to determine our range. Okay, so if we don't care about the first 10 bits, let's say if this guy is if 10 is 1 and this one is stays 0, then it's going to be, okay, that's the 1s, 2s, 4s. So it'll be 4. And we know this is always 2 over here. So it's going to be 4, 2, 4, 2, 4, 0, 0, because we don't care. 2, 4, 0, 0 to 2. Well, that can be 1. If these guys are 1, that's going to be 7. So 2, 7. And if those are 0s or 1, or if they're 1s, it'll be FF. So 2, 7 FF. So it's 2, 4, 0, 0 to 2, 7 FF. That's one of the ranges. Okay. Now let's take and say 11 is 1, and that's 0. If this is a 1, it's 8, 2, 8. That'll be 2, 8, 0, 0, right? So if this stays 1 and everything else goes 1, it'll be 2, 8, 0, 0 to 2. And if this is all 1s, it'll be 2, F, F, F. So that range is 2, 8, 0, 0. No. Hold on. Hold the phone. This is staying 0. This is going to stay 0. So you got 2, 8, 0, 0 to 2. And if this is 1, 1, 1, that would be B. So the next range is 2, 8, 0, 0 to 2, B, F, F. Okay. Our next range is going to be, what if both of them are 1? Then you'll have 2, C, 1, 1, 0, 0, 2, C, 0, 0. And those two are 1. So if these two are 1 as well, it'll be 2, F, F, F. So the next range is 2, C, 0, 0 to 2, F, F, F. So we have 4 ranges to choose from. You got, depending on these two guys, you got 2, 0, 0, 0 to 2, okay, you got 2, 0, 0, 0, and keep these 0, and if the rest of them go 1, then you got 2, 3, F, F. So the first range is 2, 0, 0, 0 to 2, 3, F, F. And then if this guy switches to 1 and this guy stays 0, then you got 2, 4, 0, 0 to a possible 2, 7, F, F. And then if this guy goes 1 and this guy stays 0 the whole time of the range, then you'll have 2 8 0 0 to 2 B F F if that stays 0. 1 0 1 1 is B. And the minute that this switches to 1 and these are both 1, then you've got a new range, 2 C 0 0 to 2 F F F. Okay, that's a long way of explaining that with this many RAM chips, you can have 4 ranges. So if we now go on the Fluke and we go, okay, RAM short, let's do that first range, 2000 to 23FF. Now this is testing only 2 of these chips. We don't know which 2 yet. Okay. Those 2 chips that it just tested are good. Now we're going to go on to the next range, which is 2 chips. And that's going to be 24 to 27FF. This is where our bad chip was, remember? Bit 20. That's telling us that 1 chip is bad. There's only 1 bad chip, and it's the high bit of this range. It's the high 4 bits of this range. So let's skip that range and let's move to the next range, which was 28 to 2 BFF. And this is testing 2 more chips. Okay, those both are good. And the last range is 2C00 to 2FFF. This is the last 2 chips. Okay, now let's go back to that bad range. It was 24 to 27FF. Okay, there's our error. So how do we tell which chip that is? Okay, we determined that we have our 4 ranges, right? These are our 4 ranges. We're calling them A. This range right here is A. This range is B. This range is C. And this range is D. Okay? All right, so by going back to this, and we know the address 10 and 11 is what determines our range. Sorry, just pulling the schematic back behind me. Okay, sorry. Okay, so if we have a 0 and a 0, that is going to be, that's going to be 0. So it's going to be 2 0 up to 2 3. It'll be 2 0 up to 2 3. So 2 0 to 2 3 is A. So if they're both 0, then it's going to be output A. It's going to be range A if they're both 0. Okay. Now if address 10 is 0 and address 11 is 1, if this is 0, then it's going to be, if that's 1, it's going to be 8. So 2 8 up to 2B, right? 1 1 1 up. If that's 1 and that's 0, it's going to be 2 8 up to 2B. So that is B, 2 8 to 2B. So this scenario is 2B, or is B. Now if 10 is 1 and 11 is 0, if that's a 1, it's going to be 2 4, right? 1, 2, 4, 8. So it's going to be 1, 4, and that stays 0. 2, 4 to 2, 7. 1, 1, 1. 2, 4 to 2, 7 is C. 2, 4 to 2, 7 is that scenario. And the last scenario is both of them 1. And if both of them are 1, then you'll have 2C, 1, 1, 0, 0, 2C to 2F. Is it 1, 1, 1, 1. 2C to 2F, which is right here. That's D, 2C to 2F. 1 and 1 is D. Okay, so if we look at our schematic, and we've determined that 10 and 11 are what are going to trigger our RAM. So if we go back to this and say, okay, 10 is 0, 10 is 0, 11 is 0, and that gives us A, which is 2000 to 23. So if this is 0 and 0, and we know these are 0, so that's 0, that's going to enable VRAM 1. So if there's 0, 0, it's going to enable VRAM 1. Now the next scenario, we got 10, 0, and 11 is 1. So if 10 is 0 and 11 is 1 in binary, this is the most significant bit. So that'll be 2, 0, 1, or actually 1, 0. That's the most significant bit here. So that's 2. So it's going to do 1 or 0, 1, 2. VRAM 2 is enabled. VRAM 2 is enabled when address 10 is 0 and 11 is 1. Now the next one, you have address 10 a 1 and 11 a 0. So when 10 is 1 and 11 is 0, that's going to fire 1. 0, 1. That's least significant bit. So in that scenario, it enables this guy, VRAM 1. So you got VRAM 1 when 10 is 1 and 11 is 0. And the last one, they're both 1. And if these guys are both 1, it's going to fire 3. 0, 1, 2, 3, which is VRAM 3. VRAM 3. Okay? Now if we look at our schematic and we know we want C. This is what we're curious about, is C. That's our bad range. So C is VRAM 1. So we come over here, VRAM 1 enables B2 and another guy. I gotta move it over. Bear with me a second. Sorry. Okay. Oh shit, what just happened? Okay. All right. Which one did we say? VRAM 1. This is the one we were curious about? Yeah. VRAM 1. So we're going to look at B2. We're going to look at B2 and B1. And it's the high bit. Remember, it's the high bit, right? So this side right here is the high side. Here's data bits 4 through 7, and over here is data bits 0 through 3. That's these guys, and these guys are the high ones. So we're looking at B1 as our bad RAM. B1 is our bad chip. This guy right here. So I am going to go ahead and replace that guy, and then we'll verify that our schematic breakdown was correct. But before I do that, just keep in mind, remember, B1 is the one that we just figured out was bad. This also has problems with the range 0 through 3FFF, or 3FF. These program RAMs are jacked up. Oops. Yeah, now it's saying that bits D0 are tied. Oh, now it's not tied. Yeah. Yeah, that high bit DC. I think I have a bad buffer because it's kind of random. I think that's a buffer, a data buffer problem. But one thing at a time. I'm gonna fix this guy first. Okay, guys, we're hooked back up, and I rearranged how I had everything. I didn't like how I had the Fluke over here, so this time I'm doing it this way. Anyway, I replaced B1. If you remember, that's one we said was bad. I got it socketed and replaced. So, and that range, if you remember, was 24. So let's do 24 to 27FF. And now we're good to go. So we'll cover the whole range now. This is that whole range. 2002 FFF. And I'm going to have to look at the schematic again, and I'm going to find out the program RAM. I believe the data buffer back to the CPU, from the CPU to the RAM, is bad, and I think that's a shared. I think the data buffer for that is shared with the ROM, so there's no way this thing's going to run with a bad buffer like that. So I'll look at the schematic, find out which buffer that is. We will hook the system up completely, and we'll put our analyzer on the buffer. And we'll analyze that data buffer, because I suspect that it's no good. And that whole RAM range is now good. Excellent. You know what I'm going to do? I'm going to get the... Let me do this. I don't know if this is even the right range. This is... I think this is the vector ROM. I'll recognize the signature if it is. That is 6628. That is vector ROM. I remember that signature. Let's do the next one. I'll remember this when I see it. That's it. F6EA and 6628. Those are the two vector ROMs. F6EA. That was it. So we got a good path. Yep. We have a good path to all of the vector ROM and RAM. That's all good. The addressing's good. Everything's good to go there. So we'll go ahead and unhook the Fluke. We'll put the system together completely. I'm going to put my analyzer on the data buffer to the program ROM and program RAM. I believe there's a bad data buffer. So let's look at that. Well, as you can see, I'm on that data buffer. This is the data buffer. It's a 245 data buffer from the program, ROM, and RAM to the CPU. And I got it up on here. And you can see I got the enable line, the direction line, and the A bus and B bus. And it's enabled low. So these two lines should match when it's 0 up here. And they do. Always. The curious thing here, I've got it triggered. I'm triggering on the direction going, any activity on the direction line. And this is all I'm getting is this little blip. But you know what? That might be normal, because this thing is watchdogging, remember. And it's not going to run right. And this doesn't have a watchdog disable. So for all intents and purposes, I don't see anything wrong with this buffer. So yeah, we got ourselves a mystery here. It's more than likely it's probably a decoding error. So we'll have to go back to the schematic, back to the old drawing board, and put the old thinking cap on, because it's probably a decoding error. Because it's pretty straightforward. It's this data buffer looks proper. It looks okay. The address bus I know is good because the same address bus goes out to the whole system. It goes out to the RAM and everything, and that's okay. So yeah, so we've got to have some kind of a decoding error. Alrighty, well I'm gonna take the Fluke or the I'm gonna take the analyzer off of it and start poking around with the logic probe and see if we can come up with some, find out where to go. Okay, what I just did really quick was I had it hooked up, and there is watchdog disable right here. And I hooked that to ground so that there was no watchdogging going on. And I took my oscilloscope and I was probing around. And the way most Atari boards work is they'll have one ROM, and it's usually the highest ROM. Because I believe the 6502's boot vector is FFFF, which means it'll go to the highest ROM, which is this guy. And when I unhooked watchdog disable, the enable was laying low, which is expected, and the others are all high, which is expected because this is going to boot and it's going to get its initial instructions from this guy and then start running code, right? But it's not getting anywhere. It's just laying there. And when I tried to read these ROMs with the Fluke, I kept getting random data errors, and it would say that bits were tied and stuff. I didn't show you that, but that's what was happening when I was trying to read these guys. So what I'm thinking I have a hunch that these two RAMs are bad and they're messing everything up. So in any way, it's kind of a process of elimination thing. I'm going to pull both of these RAMs, and then I'm going to put the Fluke on it and see if I can get to these guys. Because these RAMs and these ROMs dump their data right onto the same bus. They're straight connected to each other. 8 bits from here and the 8 bits from these guys are straight connected to each other. And then they go through this guy back to the CPU. So the CPU sends its data here to both here and here. And then these guys and these guys send their data through here to here. So that's the path. And then there's the decoding to fire everything. But I'm going to make sure that the data is not corrupted. So I'm going to pull these guys out of the board completely. And then I'm going to hook up to it with the Fluke and do ROM checks. See, that'll tell me if it's decoding. So right now I just want to eliminate. I want to eliminate funky data bits. So, all right, I'll get to it. Okay, I had pulled out the 245 data buffer for the ROMs and the program RAM. I pulled that 245 out, put it in my chip reader. It tested good, which I suspected it would. And I also pulled out another 245 that actually passes data over to the auxiliary board. I pulled that one out just to kind of isolate the data bus. And they both tested good, which I kind of figured they would. So now I'm doing ROM checks on my ROMs. And I've got this guy in the board. 036412. And you can see it is not in backwards. The notch is right there. And it is saying backward device. So I'll try to load it into RAM. Load RAM from master. And you see it's kicking backward device. So this ROM is no good and is mucking up the works. So I'm going to go ahead, finish dumping the rest of these guys, and then verifying them. And I'll have to burn a new one at least. So this is enough to mess up the whole system right there. One bad ROM. So, okay. I'm going to go ahead, continue with the rest of the ROMs, and burn this guy and a new one, and continue on. Okay, I ended up having to replace 5 ROMs. Some of these just flat out had bad data on them. Some of them would dump the proper file, and then I could never verify it to that file, even after cleaning the legs. It might verify once out of 10 times, just a flaky ROM. So I ended up burning 5. I'd say 2 of them were just bad data. One of them was absolutely blown out, remember? And then a couple, 2 or 3 of them, I can't remember which, would dump the proper file and then just would not verify consistently back to it. So I ended up replacing 5 ROMs. So, all right. We are all hooked back up. I'm gonna turn that off, plug this in. We're gonna fire it up together. I did socket these guys because these are CMOS. They're 74 HTC 245s. It's just a different construction, same operation. But CMOS chips I always socket because I don't like soldering those because they're a little more susceptible to heat, I think, than TTL. So I socketed those guys, and I got all the ROMs in it. Let's see, this is new. new, and both of these guys are new. So let's go ahead and fire it up. And I replaced the LED because I don't like it when that stuff, little details like that don't work. All right, we're still spot killing, so it's still not working. Let's go see if test does anything for us. No. Okay, we're still not getting anywhere. Alrighty, so now I'm going to put the Fluke back on it and see if I have any access to these guys. And this program RAM should be fine now. So I want to test that. My Fluke does not work great for ROMs for some reason, but it works. That 6502 pod works great for RAM, but it's kind of flaky with the ROMs, so it might work. I don't know. But I'm going to go ahead and put the Fluke back on it. But first, I think I do want to check the reset line. Let's see if our reset line is resetting. And it still is. We're still resetting. Okay. That's okay. So we'll throw the Fluke on this guy and see if we have any access to this stuff. Hopefully it doesn't give us back 5CD7, because that means there's nothing going on. If the Fluke gives me some randomness, that'd be great. But the 5CD, 5CD97 or 59C7 or whatever it is, just tells me that it's not getting anything. So let's do that. Let's pull the Fluke out, put it back on it, see what we get. Well, people, this is not how I envisioned my Saturday. Well, the water heater's out, and I got it cleaned up pretty good. I want to say thank God for shark bite fittings. This guy right here, because that guy does not work. It's stuck open, cannot close. And then I go to turn off the main supply, and the main supply valve does not close completely. I had a pretty good flow coming out of the cold water, so I had to cut it and put a shark bite fitting in. So thank God for shark bite fittings. I was just taking a look at this PCB. I removed the socket here as I'm putting a new socket in it. This, I just went like this. Look how dirty. This may be one of the dirtiest PCBs I've ever seen. And it looks like it's got brush marks, like someone was brushing the dirt. I don't know. It's very strange. I'm thinking that I might just go ahead and wash this board right now, as it is really, really bad. Super dirty. But I probably won't do that just yet. I will eventually, but I want to replace this because I want to do some testing on it before. I don't really want to wash anything right now anyway. I've been working on my water heater went out today, so I've been dealing with that all day long. So yeah, I just wanted to point this out. This thing is so dirty. I mean, I can't believe how dirty it is. It's weird. It's gonna be fun to wash though. But I won't have no hot water till tomorrow, so I'll wait. All right, I'm gonna go ahead and put a socket in here. Good Sunday morning, everybody. I'm back at it again. It's I've been up and at it since about 5:30 this morning. Anyway, what I did was I programmed a complete matching set of ROMs, and because I noticed some of them were a different revision than the other ones that I had burnt. Whatever. I burnt a complete set of matching ROMs revision, and I got it on right now. As you can see, it's doing nothing, just a dot in the center of the screen. But what I want to show you is I believe our program is running. We're out of reset. Of course, the clocks are good. Okay, read write is now doing nothing. These are our ROM selects. I actually think I have this thing in test. This is test. This is regular running, I believe. Oh, come on. Okay. Yeah, I don't know. It's hard to tell if the code's actually running or not. It's not in reset. We're getting nothing on the screen. We have activity on the ROMs. Not on that one, though. Not on that one. Or that one. It doesn't look like it's selecting all of the program. So, yeah. Strange. Okay. Yeah, I think I'm going to have to put the analyzer on it, and I'm going to go over the entire decoding, the entire decoding circuit, and just make sure it all looks correct. Because right now, you know what I need to do is I need to pull up a, I'm going to pull up a pinout of this guy. I'll just look at the schematic and go over all of the control signals to this guy and make sure that they're looking good. And then move on to all of the decoding circuit. Well, I just took time out to wash this board because it was filthy nasty. And I cleaned it up, and it's about 100% better. Okay, I got it populated and everything. If I take my logic probe, right now I have it just running. It is not in test. Test is up. I was confused about that earlier. This is normal running. And we have no reset. We have We have all kind of ROM access activity. What about these guys? Yep. Yep. Okay. All of the ROMs are being accessed. We are not in reset. I believe that the program is executing fine. We just have no output at all. You'll see. Hey there. We have no output. And that is I don't know if you can catch that on this camera, but that is not a perfect, just dead spot. There's actually activity in there. I can see in that little dot flickering and stuff. So this program is running. I'm confident of that. So it's just a matter of tracking down why there's no vector output. The CPU side of it, I believe, is A-OK. So I'm going to start looking at the schematic for the, the state machine stuff and the timing and control and all that business. And see what we can't find. See if we can't find something going on that isn't supposed to be going on, or something that's not going on that is supposed to be going on. So, alrighty. Well, I'll be back. Okay, I'm kind of playing around in the decoding circuitry, because I was still getting errant, just kind of random, not really random, it's pretty regular reset pulses. And so I'm going through the decoding to make sure, even though this looked like it doesn't always look good. It doesn't always look like it's running. So I am going through the decoding, and I'm on a 139. I'll show you the guy I'm on. It's right here, C4. Gets its inputs from the address bus, buffered address bus, and it's enabled off of another 139. So I'm onto that guy right now, and that produces right here is input output, and then this goes to a gate that enables the other another 139, another one, and RAM, CPU RAM. So let's take a look at that guy. Okay, we're back. Okay, I got it running free right now. And you can see, let's stop it. Let me try to stop it on when it's enabled. There we go. Enable is low, so it is enabled, and it's selecting 3 this whole time, and 3 is low. So that looks good, right? That's good. Okay. Here it is disabled, yet you have low pulses on the second line. That is not correct. That should not be there. So there's something funky going on this line, line 2. It goes away when it is enabled. And line 3 is staying low even when it's not enabled. When this is disabled, line 3 is staying low. If you see that. See, this thing's goofy. It's not working right. No, this thing's definitely going to get replaced. Yeah, that high line, even when this thing goes disabled, that's supposed to go high. And it's staying low. So yeah, that ain't right. So I'm gonna go ahead and replace that guy and see what happens. Okay guys, I did replace this guy, and I'm in test mode, and of course I got the little dot there. But the good news is, even though I am in test mode, I have, you can hear you hear that? That's switch test. Those are the coins, and then these are the other switches right here. So that's switch test. So this thing is actually running the program. It just doesn't have any output, no video, no vector output. So we're going to have to start looking into that. But I think program-wise, I think we're pretty good. I think we are good program-wise. So I'm going to stop with the decoding and all of that, and I'm going to move on to the vector generation part of this board. Because I'm convinced now I can go into test mode and I can do the switch tests and I can hear it and stuff. So yeah, so we're going to move on to vector generation. Okay, I moved on to looking at the vector generation part of the schematic. And this is the program and stack counter. It basically starts the hardware's access to the RAM, to the vector RAM. In not so many words. Anyway, this counter is what starts these register files producing signals that move over and create the signals that go to the addressing muxes. Okay. And this guy gets these control lines. All of the inputs are grounded, so when it loads 0. So it starts at 0, and it's either going to go up or down according to this guy, this signal. This is an enable signal. And then you got a couple control signals here, load and clock. So if we come over, that's J6. Come over and take a look at J6. It's this guy right here. So if I take a look at my output bits on 2 and 3, here's 2. It's always low. And here's 3, which is also always low. Now we'll look at control lines. Here's the enable. Enable is always high. So we have no enable. And then this is the up-down line. The clock is right here. So there's your clock pulse. And 11 is another signal. I'm not sure. The load signal, I think. So you got all of the control signals except for the enable, and if this is never enabled, it will never count. So pin 4 of this guy is the enable, and I need to find this signal right here, OP2 bar. So let me dig around the schematic and find where that is made. Okay, now I have found all of these control signals. They come from this 175 latch at K8, and it's controlled by the clock signal here. Comes from these latch signals, and I know that these are made from the state machine. So if that's missing, I'll go to the state machine, that signal there. So what we're going to do is I'm going to look at this guy. First I'm just going to probe it around, and then we'll analyze it and make sure that this guy is doing exactly what it needs to do. So let's do that. Okay, I'm going to go ahead and hit K8, and I'll call out the signals. Pin 9, I'll look at pin 9 first, and that is the clock signal. That, remember, comes from the state machine, the latch signal. And there it is right there, so that looks good. That's no problem. Now we're going to look at our inputs to this latch. And those inputs are on pins 4, 5, 12, and 13. So here is pin 4, right there. Pin 5, oops, I shorted it. I'm going to hit reset. There's pin 4, pin 5, 12 and 13. Here's 12 and 13. So we got good activity on all of these data lines. These are basically the data lines. And remember, this is our clock signal. Now I'm going to look at the outputs. The outputs on this are pins 2 and 3. Here's 2, and here's 3. Okay. Then you got 6 and 7, which 6 is always high, so 7 is the inverse of that, which is always low. And this is the input that is being latched there. So what we'll have to do is analyze this and see if it's supposed to stay high all the time. It might be right. Okay, now we'll go to 10 and 11. This is output and output. And 14 and 15. It's output and output. And that's input. Shorted it again. I'm really curious about this one right here, staying high. So let's analyze that. I'm going to hook the analyzer up to that guy, and we're going to see if it's doing what it's supposed to. Okay guys, this is analyzing K8. It's a 175 latch. And you'll see here I have the enable line right here. Then you got data in. And Q and Q bar. So right here we're chugging along and you get in you get a clock pulse. And on this rising edge, this line is going to clock to this line. And it's 8 instead of A. Okay? This should say A. And it says 8. Kind of want to catch that little change. It don't matter. But you can see I'm going to put it into test. I want to do that again and check this out. Okay, here we have, we go to the delay. Okay, got a couple deals here. You got a clock pulse here, and it says A, but down here on the Q line you got 8. And the inverse of 8 is 7, and I'll show you that. You got another enable here, clock pulse. On the rising edge, C should go, and it does, C3. So I wanna write that down, because we're gonna take a look at this. C. And the inverse, it says, is 3. Okay? All right, so let's take a look at what we got here. What is this telling us? Okay. Remember, it's data, the data line was A, and when it was clocking, Q line said 8. So what that's telling me is this bit is stuck 0 right here. If this bit is always low, then that'll stay 8, right? And the inverse of 8 is you just flip the bits, 0, 1, 1, 1. So this Q bar should have been B, because this should have been 10, or this is 10. This should have been the inverse of this. Well, this should have been, that should have been A, that line. So Q should have been 0, 1, 0, 1. Q should have been 5, 4, and 1. So this should have been 5 instead of 7. That should have been 5, but it wasn't. Now we've seen when the data line was C, it clocked over and Q line was C. It was right because this line is already 0. So it didn't change. And then the inverse of C, you flip the bits, is 3. So this chip has a stuck bit right here. So this is going to have to be replaced, this 175. So let me get to that. Okay, and here you can see I have that chip in the tester, and it does come up with a fault. This IC tester works good for simple gate chips. It does not work good for, what doesn't it work good for? It's kind of flaky with 367s. It works good for most chips. So it's actually a pretty good tester. So yeah, but the analog CMOS chips, like the 4016s and 4006 and stuff like that, even though this can test those, and I wouldn't really trust this with op amps, but you know, standard TTL logic, this is pretty good. Okay, there is the new K8 in the board. As you can see, we got more of a something going on. It's kind of, you'll see it kind of shoot stuff around a little bit. It's still got some major failure going on. But it is doing a little bit more. So it's trying to do something. But if we look at K8, this guy right here, this was that stuck bit right here. And you can see up here, it's no longer stuck. This is that bit that was stuck, and here's its inverse. So now we are getting that signal. So that's good. Now I want to go back to where I was at when I found out that this was missing a signal. Go back there, work that vector generating. I want to make sure that the hardware going through that paging system is getting to the RAMs right. Because if they're not, then this is going to be, it's just not going to work. So I'm going to go right back to where I was with that counter, that 191 counter, wherever it was. I don't remember where it was. But make sure that is running that stack and program counter correctly. So we'll get back to the schematic and get back to where I was. Okay, so now that we've got that 175 at K8 fixed, remember this was the signal that K8 produced that was missing, is this enable line. So what I'm going to do now is I'm going to start right here, and I'm going to check out these two clock signals. I'm going to look at the signals coming into this, the signals coming out of this. I'm going to look at these gating signals here. These are control signals here. This signal here. I'm going to look at this 367 driver and just probe the inputs, probe the outputs. If anything looks suspicious on these guys, they're both 367s. If anything looks suspicious, we'll throw the analyzer on it. Now I'm going to come over and I'm going to look at all of these lines on these 193 counters. So that's what I'm going to look at right now, is this whole section right here. Okay, I'm going to go ahead and switch on. And I'll be looking back to the schematic on the TV back there. Yeah, see, we got our little business over here on the screen. I don't think you can see that right now, but that's not important. It's just garbage. So, oh shit. Zoom this up. Okay. Okay, I want pins 2 and 3 on J6. J6. Pins 2 and 3. Okay, those signals on J, those 2 clock signals look perfect. I'm gonna check reset out for about a minute and make sure this thing isn't resetting at all. It's not resetting, it's running. Okay, good. Very good. Okay, moving on. I want to look at pins 1, 2, 3, and 15. 1, 2, 3, and 15 of row 6. Row 6. This guy, these guys right here. E, F, and H. E, F, and H. Yep. Pins 1, 2, 3, 1, 2, 3, and 15. Same thing. 1, 2, 3, and 15. Okay. These signals all look good, which is good. That's the inputs to that. And they all look fine. Okay, I want to check these other control lines. I want to check lines 11 and 12 on these guys. And it goes to all of them, so 11. 11 looks good. And 12. And 12 looks good. It's definitely a signal. Those signals look good. Moving on. 11 and 12 look good. I want to look at these 367 drivers. H7 and F7. H and F7. These two guys right here. So, okay. 1 and 15 is attached. I'm just going to have to make sure I have an output. Those appear to be okay. So we'll move on. H5 is what I want to look at now. H5. I want to look at H5 pins 5, 11, and 14. 5, 11, and 14. Yeah. Okay. Looks pretty good. How's about our carry bit on 12? We should have a carry on 12. H5. And do. But it's a low carry. It's a low pulse carry. Strange. Okay. 2, 3, 6, and 7. Each 5. 2, 3, 6, and 7. That one seems to be just fine. These are all loading together. 14, that goes together. So F5, check 12. F5, check pin 12. Okay. Those seem to be good. Those don't seem to be an issue. Okay, I'm going to cut the video for a minute and look at the schematic again, because everything in there seems to look okay. So I'm going to move on. And if I go through the whole vector generation system with everything looking good, then I've got to go back and actually start to analyze things. Because even though something looks okay, doesn't mean it's okay. Right now, I'm just scanning through and looking for either floating outputs or stuck bits that look funny. So, all right, I'll be back. Okay, I am in the state machine, the control to the state machine actually, and I'm looking at this mess right here. M7 is an O2, and it's basically acting like a latch. And the inputs are from this guy here, which is a 74, inputting pin 2. And then the input for this part of it is on pin 6 here. And it comes from N7, which is an LS27. And you'll see our signals are vector memory, state 2, and that's right off the state prom. And I already probed that and I know that's there. And pin 13, which is also this line right here. So I'm going to look at this guy. I'm going to probe 1, 2, 13 out to 12. Right there. 1, 2, 13 out to 12. So if we come over here, and the guy in question is right here. This guy right here. So if I go pin 1, here's pin 1, pin 2, and 13 is right here. And here's pin 12. Pin 12 is just low. It's low all the time. And it could be. I don't know. I find it suspicious that that output is low all the time. So we're going to hook up our analyzer to this guy and see if that output is supposed to stay at a low state. Okay, guys, as you can see here, I'm on that LS27 that was in question. It's a 3-input NOR gate. And I'm going to bring the camera down here. I'm going to show you the truth table on a NOR gate. I wrote it out so that sometimes I just have these NOR gates and NANDs. A lot of times I have to write out the truth table because I get confused with the simple NOR gates. It's really, I don't know why, I just do. So I write out the truth table. And you can see on a NOR gate, the only time that the output will be high, or a 1, is if all of the inputs are 0. That's the only way you're ever going to get that to go high, is if inputs A, B, and C are all 0. So what I'm doing here is I'm triggering on my 3 input bits at 0, at a hex value of 0. As you can see right here, I've got it triggered at 0. And as we said in a NOR gate, the only time that this will be high is if these are all 0. And you can see it's going 0 here, it's 0 over here a little bit. Your inputs are changing and hitting 0, and this should be going high. This whole time this is 0, this should be a high pulse. So we have another bad chip here. This is an LS27. I'm going to have to go ahead and replace that guy. So we will go ahead and get to that. Okay, I have replaced the 27 and I re-hooked up to it just to show you the proper operation of this chip. And like we had talked about, here I have once again the inputs and my output. And you'll see when it's 0 is when you get your 1. That's how it's supposed to work. So that was definitely bad. But the problem is we haven't really made a change. It's still the same nothing. So I can see the program running in there. This thing, I can see it running. There's just some kind of a failure. We'll find it eventually. Just got to keep digging. So okay, well, that's one step closer. One bad thing replaced. We'll keep moving. Well, it's probing around again, and I came to this 109. You come over, we'll take a look at it. It's this guy right here. It's in the vector section. It just creates vector center, inverse of vector center. They go over to the timing. they're timing signals, I believe, in the timing section. Yeah, so this guy also has a second side, which I should see what that does, but based on this one side, come over and take a look at this guy. It's getting its inputs from stop, and this is coming from another gate in that LS27 that I replaced. So that should be fine. The 12 megahertz clock. And I'm not exact. Oh yeah, that's from the 27. And the stop signal. Halt is our clear signal. So let's come over and take a look at it. If we come up here, I got a snapshot of it. And I will get the truth table. This is a kind of a JK flip-flop is it's a little more complicated than your regular old flip-flop. These are the only in preset. The preset pin on this thing is pulled high with a resistor, so this doesn't really matter. It's just whenever clear is high is the only time that we're going to expect something. In here, I've got a snapshot of 1-1, and it clearly states that Q should be 1, Q bar should be 0. And if we look at it, I got this snapshot here. J is 1, K is 1. Q should be 1. See, Q's kind of just got some nonsense going on, and Q bar is always 1. So this thing is not working. So here's another one that I'm going to have to replace, this 109 right here. Hey guys, check this out. This is a 109. I've got jumped on that one I was just analyzing. I just, for S's and G's, I just took a 109 and jumped it over it. And check out the screen. There's Battlezone. So I'm going to go ahead and properly replace that guy. Put that 109 in the board, and then we will put this up on the real monitor and see how it looks. Okay guys, unfortunately my black and white vector monitor decided to the high voltage decided to quit working, so I can hear all the vector chatter and there's no spot killer, but there's no high voltage, so I'm going to have to settle for this guy. We'll go ahead, I got that chip changed out, and we'll go ahead and fire it up. Okay. Turn that light off. What I'm going to do is put it in test. Yeah, you can see a little bit of flakage. These sockets are junk. That is what the problem is. I can mess with the I can mess around with the chips and stuff and it straightens up. Yeah, that looks like crap. That was just bad connection on those. Yeah, it's on the math box. It's just bad sockets. So I'm going to go ahead and clean chips, clean chip legs, clean sockets, all that good stuff on the math box. Okay guys, I had my black and white vector monitor hooked up because what I got going on here is these 4-bit processor chips right in here are all bad, I think. Because if I take them out, I get a solid grid pattern screen. And it never flickers, never goes away, nothing. It's there solid. If I have those chips in, it just goes all flaky, all kinds of flaky. So yeah, so I've got them out right now so that I can work with this test pattern. But what I was being thrown off because I had my vector monitor plugged into this thing and it wouldn't have no screen, and I'm like, okay, my vector monitor took a crap, you know. So I started messing around. I put a new high voltage diode in it, and it's getting high voltage. It's working as it should, but there's no picture. So I was kind of scratching my head, and then it just hit me this morning that I better check the Z intensity circuit, because that'll turn the beam completely off. So what I've done is I'm going over this Z circuit right here, Z. And first chip I'm checking is this 175, and it has all stuck outputs. It has a good clock, it has good moving inputs, but all of the outputs are stuck. So I'm going to put the analyzer on it and look at this guy right here, F8. Okay, this is that 175, and as you can see, I have it here with the clear signal is always high, so it's never clearing. And then you got the clock. There's your clock pulse. Data is at 4, so it should clock 4 to the output, and it's just stuck at B. No, this guy isn't doing anything. And you can see the input changes now and again. It goes between B and 4. And I imagine if this was out of test, you'd get a lot more changes on that data line, but it's just kind of stuck right here for this particular screen. But this doesn't do anything. So that's going to have to be replaced. You know, I put those chips back in the board. I put these guys back in the board to, now you'll see more movement. And you can see this thing isn't clocking anything over. This is changing a lot. And it's just stuck right at B. At this rising edge right here, whatever's on here should go down here, and you can see it doesn't. So yep, that guy is gonna have to be replaced. Okay, I replaced that 175 that we were looking at, and it was definitely bad, but it did not fix my Z intensity problem completely. So I went probing around in the Z amplification section again, and I came up to Z1, which was floating. This signal right here was floating. And this is in the analog vector generation part of the schematic, because I had to find out where these signals were made. And it's another 175. It's another junk 175. So we'll go and let's probe and look at this guy. J8. And you know, this is deceiving because this is up on my, it does not work on my vector monitor, but it works on this. Because this thing disregards Z completely. All this thing cares about is there X and is there Y, and it displays it. The vector monitor uses Z intensity to shut off the beam according to the level of intensity. And right now I believe my intensity is just grounded. There's no intensity, so there's no beam. So J8 is this guy. This is the one I just replaced. We'll take a look at that one really quick. Some of the outputs are on 2 and 3. You can see I have outputs now. This is 2, this is 3. So that's definitely good now. And this is J8, the one that was just on the schematic. This is the input on 4. And here's the output. Stuck low. And its inverse is, they're both stuck low. Oh, there it is. Now it's high. Yeah, that one's stuck high. This one's stuck low. Yeah. Yep, so that guy's got to be replaced. So we'll go ahead and replace that guy. I might hook up to it and analyze it just to show for sure. But pretty sure we got another bad. 175s are the winner on this board. Okay, I'm going through all of those 175 latches, and what I did was I pulled up the manual and I looked at the parts list, and I've already replaced 3 175s, and there's only one more, and I found out where it is, and I probed around on it, and it's got a stuck bit. So I'm going to have to replace that one too. So that makes 4 out of 4 175s on this board no good. But unfortunately, I'm out of 175s, so I've got to order some. But anyway, I'm looking at the Z blank signal, which is gated right here. And the inputs to this are this guy right here. Input that to create Z blank, and a signal up here. But right now, I'm just looking at these flip-flops. This guy right here in particular, J10, the high side of J10. So if we come over and look at J10, and remember this is Z blank. J10 is right here, the high side. Our clock comes in on pin 11, which is 8, 9, 10, 11. There's our clock pulse. And I'm going to move over to the data signal, which is right here. So we got a good data signal, good clock. And if we look at our output, it is stuck low. And the Q bar part of this output, which is not connected to anything, but it should still be driving high, is kind of half-ass high. So we got a 174 here that's no good. And that's involved in Z blanking, so got to replace this guy right here, J10, 170, it's just a 74. This is the other 175, And I probed around on it, and I'll show you, it's got a stuck bit. One of the bits is stuck on it. It's this guy right here. This is the data signal, and its Q output is stuck low right here, and its Q bar output is stuck high from this data signal. So 175's got to go, and J10 LS74. And the mystery continues. I replaced this guy, and it was bad, but I'm getting the exact same behavior out of it. This is always low, this is always high. These right here, this guy right here, I'm kind of curious about, because this is actually a signal off of a op amp, basically LM319, and it's pulled high, so it needs to drive low, right? Now, you got an always low coming off of here, and I've got an always low coming off of here. Why is this always low when it's pulled high? It's kind of curious. I'm kind of wondering if this is pulling things low, this guy right here. I just got a always low coming out of here. Z blank is always low, which means Z is always blanked. So I'm looking at this, and I'm looking at the clock signal, and the clock signal doesn't do much of anything. I'll show you. This is that 74. Okay. So you got, this is the clock signal up here. This is the data signal, and this is Q, which is always low. And the Q bar, which isn't connected to anything, but it's the inverse of Q. And you can see up here, I got my data lines going up and down and up and down. This guy isn't doing much of anything, this clock signal. I'm kind of curious about that. And I know the flip-flop's good, I replaced it. So I got to kind of move backwards from that. Why is this clock not clocking this data line? Why is... Okay, those are my two questions right now. Why is this clock not clocking this data line to toggle? Oh, Jesus. What the hell happened? But you get the point. Why were those two things always low? That op amp, that signal coming off the LM319. So I got two lows going into an LS86. Two always lows. You're always going to be low. That's always going to be blanked. So that's the mystery right now that I'm working on. So I think what I'm going to do is I'm going to look at this signal right here. These two signals going into this 32. I'm going to check this guy out, see what's going on there. Just kind of move backwards. Look at this. Yeah, so, okay. Okay, I'm taking a time out to do a little bit of maintenance work on this thing. I'd have this thing running and testing it, and the video, the vector video would just disappear on my scope here, and I'd get the dot, and I'd sit here and I'd mess around with these, and I'd press on them, and it'd come back, and it'd start flaking, and it'd disappear again. I press on one of these, and it comes back again. And I have cleaned these. I've used deoxit. I've cleaned the legs on the chips. These things just need to be replaced. So that's what I'm taking time to do right now. And later on, if I have to replace these ones, I'll do that too. But for right now, I'm just doing these guys. I got to make this board, at least this board, solid. This is a nice, easy little board. So I've already tested all the ROMs, all the PROM chips. I already put them in my reader and verified that they were good. So I'm just going to make this board solid right now. Okay, we're hooked back up. This board has been thoroughly washed and all of the 5 40-pin sockets replaced. And we are back to having a solid picture now, which is good. I had to eliminate that thing flaking out on me over sockets, so I don't have to worry about that now. So now I will continue on to troubleshooting this guy. Okay, I've kind of set up. This is a Battlezone board that I had done a previous repair on, main board. It works. And I'm just getting a view of the X, Y, and Z circuits to show what they look like on the scope. And this is the X circuit right here. Kind of strange, isn't it? This is the X output. And now I'm going to move it to the Y output. And now to the Z output. This is the Z output right here. I'm going to move it up to it's pretty weird looking. It's at 5 milliseconds. It's 20 microseconds. I'm going to go to the Y now. But these are proper X, Y, and Z signals. And I'll go to Y. And at this speed you really cannot see Y. So I'm going to kind of back it up. Slow it down. Five milliseconds. You'll see when the Battlezone text is scrolling up, you'll see this like go up really slow. Battlezone is scrolling up now, and you see this. It's kind of cool. And now I'll move it back to the X. And that's what X looks like. Looks like X is about, what, 40 hertz or something like that? Huh, interesting. I wonder if that's like every time it, you know, scans the screen or something. I don't know. I really don't know. Yeah, it must be every time. This must be continuously scanning the screen or something and doing vectors on the screen over and over. That's why you see the same thing over and over. I can only imagine. I'm not really sure how it works. Just thought this was kind of cool to show. This is Y, the Y circuit. All right, just wanted to show that. And I kind of wanted to document it. Why not? This is the Z output on Battlezone, and this is at a setting, a TTL setting. You can see the preset over there is TTL. It's just moved to 10 microseconds. And that is what your Z intensity output looks like. Well guys, just when I thought things were going good, this thing has sprung a new leak. I know it's hard to see. I don't know if you can tell or not. It's just messed up. When the Battlezone scrolls up, I'll try to come back and let you see that. But yeah, something ain't right. Something's gone funny on it. It's probably going to come up. See, you'll see this is goofed up. And there's Battlezone. And you can see it has gone funky on me, so yeah. So we'll go back to, I guess I'll just go back to the start at the the vector generation system and just start all over. Something's gone bad. So and that's kind of a funny one. I know it's not the math box. It's on this board because I just had the other board hooked up to it and it was fine. So the math box is good. It's this board. But what is it? I need to decide if that is an analog problem or a digital problem. And right now, I can't really tell. It could be either. It really could. It's funny. I have an order coming with some of this stuff. All this analog junk up here. Because I believe I need to replace these guys, because these guys are intricate in producing the Z signal. These guys right here. So I'm going to replace both of those when I get the parts. I got TLO 884s coming. This guy right here, I'm going to replace that. And I'll probably replace the two 082s and see what that does. And in the meantime, I'm going to just kind of go back and start probing around in the vector generation portion of the schematic. So, alrighty. Well, I'm going to get to that, and hopefully this doesn't take too long to find. Alright, this is very curious, guys. I went through and did a little maintenance in the analog section up here. And what I did was I just kind of raised these 082s out, the TL082s, out of the board. I tested them in my chip tester and they tested good. I socketed them and put them back in the board. I removed the TL084. I removed these guys, which are LM319s, and I just socketed them and put them back in the board. And this guy, the 084, the 084, I keep saying O, and it's not O, it's 0. TL084. This guy, I put a socket in. When I removed this chip, I'll show you. When I removed this guy, one of the legs fell right off. This chip was in really bad shape. And what I'm finding very curious is I got the board turned on right now without a TL084. And it's doing exactly the same thing it was doing before. And that chip's not even in the board now. So what that's kind of telling me is that chip failed. So I do have TL084s ordered. They are on the way. And when it gets here, I'll put it in the board and we'll see what happens. We'll see if it fixes our problem. And more maintenance. I just went through and I replaced all of the ROM sockets, because I got tired of having to fidget around to get it to act right. So I went ahead and just, while I'm waiting on some parts to come, I went ahead and just replaced all of the ROM sockets. So now I'm just going to wait for my order of parts to come in and see what we get. Okay, I got my order in from Mouser Electronics. I ordered LM319s, and I first started out, I put 2 new ones in, and I am now getting Z. You can hear that Z output. Okay, so I now have a Z output, and I deduced it down to which one was bad just by replacing them, which is kind of neat. I'm keeping the bad one. This is the bad one right here, the LM319. And off camera, I'm going to do some testing on this to kind of refresh my memory of what to look for in a bad blown out op amp, basically. I need to get better at analog electronics, is basically what I'm trying to say. But, okay, I do have Z now, and I have fixed my vector monitor, my black and white vector monitor. I had taken I took the fuse holders off of it. I desoldered them, removed them, and I used a Dremel with a round little stone. And I went and I basically ran that stone in them and polished the inside of those fuse holders. So now I have 100% connection, and my vector monitor is back to working. There was a bad connection through a fuse, I believe. So, but I'm still getting goofiness. But I'm gonna go ahead now that I got a Z output now, so that the intensity is working. I'm gonna go ahead and hook up the black and white vector monitor. You know what? No, I'm not. There's no need to. I don't need to do that right now. I need to figure out what's going on. I have a digital issue. Something has gone funky on this board. And that's what I need to figure out. So once I find the problem, then we'll hook my monitor up. But I found out I now have Z intensity, which is good. So now I'm just going to move on and find this digital fault in this thing. Okay. Okay, after doing some basic probing around on the board, I haven't really run into anything that looks suspicious at all. So I'm starting to work back from the output. And this is an X problem. If you can see, this is in test right now. This is an X-axis problem because the Y-axis, I mean, look at the box, for example. This box is okay. And then everything that fills the box is pushed over to the side. The X-axis is messed up. The Y-axis is okay. You know, this line goes all the way up proper. This goes all the way over proper too, but that might just be, I don't know why. It's hard to, okay, I'm going to take it out of test and watch. When the Battlezone scrolls up, you'll see it scrolls up proper, right as it should, up the Y-axis. But all of what's being drawn on the X-axis goes all over the place. After this screen, you'll see it. See, it's scrolling up the Y-axis proper. But on the X-axis, everything is screwed up. I don't know if you can actually see that. Intensity doesn't do anything. Yeah, so. But what I've been doing is working back in the X circuitry up here. And I think I've found my bad part. I think it's this guy right here. Right here. If I take a good one and just kind of jump it over it and mess around with it. Oops, I pushed reset. Let's see if we can. Let's see if that Battlezone scroll is straightened up at all. I think I need to make this a little bit tighter of a fit. Let's go to the test pattern. And now it's being goofy. I'm going to turn it off and turn it back on. now it's really being goofy. Oh, this damn thing, I swear. Okay guys, I'm back. I'm sorry about that. I cut the video off because this thing started acting weird, and I just shut it down. But I think something was shorted on the board. I don't really know what that was all about, so I cut it off. And what I was saying though was that is an X problem, right? How basically I got it fixed. And what it was this guy right here. The DAC. The X DAC was funky. I just I went back, and with these you can just kind of jump good ones on there, and you'll see the screen kind of flake to good, and you know, I could tell it was this guy, so that was it. I replaced that, and now we're back. That is proper. So I am going to go ahead, I'm going to go ahead and hook my black and white vector monitor up to it. Yeah, see how that Battlezone goes up now? Yeah, so let's go ahead and hook up the monitor to it. Alrighty, we have the lights all off. I'm getting ready. I got my vector monitor hooked up, and I'm going to go ahead and switch it on. Looking good. It's a little to one side. That would be the position of it, I guess. I guess the positioning pots are on the monitor. I'm not worried about that. But man, look at that. How good that looks. We'll have to look at the dip switch settings and I don't know what the dip switch settings are. I am just going to move them all. There we go. There's English. That looks absolutely beautiful. Look how good that monitor picture looks now. I put a new old stock high voltage diode in my monitor, and I hard soldered it in too, you know, because the old, if you worked on black and white vector monitors before, the high voltage diode goes in these little inline cup things with little springs in them, and they're really cheesy. So yeah, I soldered it right in line, high voltage diode, and this thing looks absolutely solid now. And I finished and replaced all of the connecting pins, the little pins that go, the trifurcon, whatever pins that go in the housings to the monitor. That all of the connections are all redone. New high voltage diode. It's a nice solid black and white monitor now. And I just removed all the fuse holders and used a stone in my Dremel and really cleaned the fuse holders so that I won't have problems with connection again. I kind of want to center this thing. I find out which pot's on the monitor. Center it, because it needs to be centered. But I'm not going to do that. I'm not going to mess with it, because this thing is centered with most games. This game, it just happens to not be centered, and I don't really care about that. But this looks absolutely perfect. This was a long repair. This thing was a mess. This board was a mess. Well, I'm going to turn the light back on. And let's kind of go over this. What did we do here? Well, I've replaced all of these sockets. I replaced all of the ROMs too. CPU socket is new. A handful of TTL chips. A handful of analog chips. All new sockets right here on this board. Those sockets are all new. Well, that's about it, I guess. Recapped it. New regulators. Some new chips here. The RAM was bad. Yeah. Well, I'm going to go ahead and let this one run for a bit. A few hours anyway. And then call it good. As always, everybody, thanks for watching. I sure appreciate it. And we'll see you on the next one. And I'll see you then. Battlezone, that is such a cool game. And I've already done tests for the sound, earlier in the repair, so it's all good. All right. See you next time.